So we mentioned gravity waves in the water tank experiment. It was an incompressible fluid, but we'll do this again in the atmosphere, a compressible fluid, especially because you probably have seen the impacts of a gravity wave on some phenomenon in the atmosphere, and you didn't even know that was gravity wave, right? So we'll go back to our displacement of parcels. So here we have Z1 and Zp, height of the parcel, and we have moved it by delta, which is just our delta Z, and we have our ideal gas applying for the parcel, pressure of the parcel at Zp divided by RTp, which is the temperature of the parcel, Tp. Right? Fun to say Tp, and that's equal to the pressure of the environment. Why? Because we are still in hydrostatic balance, so even if you move the parcel from here to here, hydrostatic balance is accomplished by making the pressure equal to the weight of the air column above. This is the trick. We have to remember that the parcel is moving adiabatically, but it's adjusting the pressure constantly. Why do we believe it? Because hydrostatic pressure seems almost always working, hence there must be processes that adjust the pressure, right? You just can take it as a reality, which it is. So pressure of the environment at Zp divided by RTp. No big trick there. So let's do the force balance again. The gravitational pull on the parcel is minus g rho p times delta A, that's the mass of the parcel, times delta Z. So delta A, delta Z is the volume, rho p is the density, and g is, so minus gm, that's the gravitational pull. So net pressure force again, pressure at the top, pressure at the bottom should equal the gravitational pull. So delta PE, delta A. So delta PE is just the difference between the pressure at the bottom and the top. Times the area, because that's the pressure. Pressure is per unit area, and you have to multiply by area to get the force on the parcel, equals the gravitational pull, and that is G rho E delta A delta Z. Right? This is, we are taking as a constant G. Why did we not change G? Because we have assumed already that our G doesn't change very much, and we're taking rho P and rho A here, and we are going to look at the net energy, net force balance. Fg plus Ft plus Fb equals G times rho E minus rho P times delta A times delta Z. Okay, so there is the environment that's in equilibrium, let's say, and you have moved the pressure, a parcel into it, and the parcel is coming from a different pressure and temperature. Even if you moved it adiabatically, you have changed the temperature, right, because of compressibility effects, and you're going to change the density because of that. So rho del, so if you can take rho p and divide, so you get rho p delta z delta A times del squared d dt squared. So basically we are doing F equals ma. Okay, this is the mass times acceleration, this is the mass times acceleration, and this is the net force, right? So F equals ma. M is rho p times delta z times delta A, volume times the density of the parcel. Delta is the displacement, so d delta dt is the velocity, and d squared delta dt squared is the acceleration. So F equals ma. That's what we did. So d squared delta dt squared then is just cancel things on the other side and move things across. You get minus g times rho p minus rho e divided by rho p. What is this expression? Have you seen it before? Of course you have seen it before. This was our old familiar reduced gravity, right? So when you are moving in an environment, unlike the ball we pushed from the hill to the bottom or from the bottom and oscillate. When you move a parcel of air, the entire fluid adjusts. So we are always talking relative to the environment. Hence, you have parcel, environment, and the relative gravity. Reduced gravity means the gravitational pull is actually reduced because it's relative to the density change, and not just, if you just take a ball and drop it, the gravity is going to act on the ball itself, whereas if you drop a ball in the water, it's not going to go all the way to the bottom because it's going to depend on the buoyancy of the ball with respect to the water. So this is essentially the relative change and its buoyancy. Anyways, long story short, we write again our ideal gas law and our potential temperature, which you remember. We put that into buoyancy or reduced gravity and write it as G over Te times Tp minus Te using our ideal gas law. And to make it a conservative quantity, in terms of a conservative quantity, we can convert this into potential temperature instead of just the in situ temperature. Okay, so for small delta, theta E Z plus delta is going to be theta E at Z1 plus delta, the height change, times d theta E dz. You know where we are going with this, right? So theta P minus theta E is delta times d theta E, so theta P minus theta E, because theta E is theta P and this is theta E, right? Delta square d squared delta dt squared, again the same expression, can now be written in terms of G over theta E with a minus sign times d theta E dz times delta, which is delta Z. This quantity here minus G over potential temperature of the environment times the environmental potential temperature gradient, the dry potential temperature gradient. I hope you can hear a lot of crows, but nonetheless is called a buoyancy frequency, n squared. So we can write that as minus n squared delta. Okay, so why is that important? Because the stability of movement, vertical movement in a stratified fluid is going to depend on the buoyancy change, and if you move it with a certain speed, you can overshoot your neutral buoyancy level, pulled back by gravity, overshoot, go back, so you're going to create a gravity wave because the restoring force is the gravity. So n squared is G over theta E d theta E dz, has the units of frequency, and you can expand the displacement delta in terms of cosine nt and sine nt, because oftentimes the movement can be along a slope. Okay, so those are the examples of gravity waves. When air comes up over the mountain, it's going to expand even if it's dry or wet, and it's going to oscillate, and when it goes up and down, the humidity can condense and form these kind of clouds, or you can get internal gravity waves over the ocean because the water is being moved up and down by the winds and gravity waves are being created. We'll look at other examples of gravity wave in the next podcast. There are some cute things that form in the atmosphere because of gravity waves. The clouds we saw is one. There is another beautiful cloud that forms called Lenticular Cloud that we will see in another podcast, or you can Google it. You can Google Lenticular Cloud and maybe you'll say, haha, I have seen it. And now you know that it's because of a gravity wave, but it's a standing pattern, and we'll see how that comes about.